So an RF amplifier essentially converts DC power into RF power. There is certain RF input with a certain power level of Pin, and there is an output power. This output power is much higher than the input power, and in fact Pout over Pin is what we call as the gain of the amplifier, and this amplifier is able to have a higher power output than the input by converting the DC power into RF power. So the input and the output are RF, whereas the bias voltage is going to be DC supply, and that is going to provide the necessary DC power. So this process of converting RF power input to a certain output using the DC power, we can define what is called as the efficiency of the amplifier. In a sense, higher the efficiency, the better the conversion of input RF power to the output RF power. So this efficiency can be defined in many ways, and one essential way is, one of the ways is to define as the ratio of the RF power that is delivered to the load, the output RF power that is delivered to the load, over the DC power that is consumed by the amplifier, over the DC power that is consumed by the amplifier. Note that typically the input RF power is going to be very weak, so this is defined as the efficiency, and it is always a percentage factor. Maybe it could be 70%, meaning 0.7% of the input DC power is converted to RF power. When it is 70%, we mean that the output RF power is going to be 0.7 times the DC power that the bias network is feeding in. There is an alternate way of defining efficiency. There is an alternate way of defining the efficiency in terms of the conduction angle. In terms of the conduction angle, and where this theta is in radians. This theta is in radians, where the conduction angle is in radians. So this is the formula. This is the formula for the efficiency in terms of the conduction angle. And now that previously we saw that the different classes of operation of the transistors, the four different classes that we saw, class A, B, C, and class AB, have different ranges of the conduction angle, with class A having 360-degree conduction angle and class B having 180-degree conduction angle. If we go ahead and substitute that in here, we can get the so-called efficiency curve that looks like this here. That is a function of the conduction angle here. And we can see that the class A amplifier will have a efficiency of 50%, while a class C has 100% efficiency. But that doesn't mean that all the output RF power is usable, because we saw that the class C amplifier has a lot of non-linearities, and the spectrally it is not pure in spectral sense. So meaning if the conduction angle is too high, only part of the signal is recovered back. The rest of it is chopped off, and that is leading to least spectral purity. Whereas class A is spectrally pure, but the efficiency you can get is only 50%. Turns out that there are other ways of defining the efficiency of the amplifier as well. The two commonly defined ways are what we call as the power added efficiency, and that is nothing but the RF output power minus the RF input over PDC. Again, in terms of percentage, it's going to be 100%. And the total efficiency is defined as another way of defining efficiency. All these four different ways are quite common, and the total efficiency is going to be the output RF over the DC minus the input RF power. Let's take a look at one example here, where the input power is given in dBm, is 2 dBm. The output power is 34 dBm of this amplifier. The DC supply voltage is 3 volts, and the current drawn from the DC supply is 2.24 amperes. And the question is, what is the power added efficiency? What is the power added efficiency, which is essentially this guy? So all that remains is to find the output RF power, the input RF power, which is already given, but we need to convert it to linear scale, and then the DC power which can be computed from the voltage and the current that the amplifier draws. So in that sense, the input power is 2 dBm, which is going to be 1.58 milliwatts. If you convert it to linear, remember that this is in dBm, so the linear power is going to be in milliwatts. The output is going to be 34 dBm. In that sense, the gain of the amplifier is 32 dB. The gain of the amplifier seems to be 32 dB, but that's something to make note, though not useful for the problem. And that turns out to be 2511.8 milliwatts. Now the DC power that is consumed is going to be, for a DC, it's voltage times the current, and that is going to be 3 times 2.25, which is 6.75 watts. So from this we can find the PAE to be the output RF power, which is 2.5118 watts, minus the input RF power in watts, which is 0.00158. Note that the input power is very low and the output RF power is pretty high, over this DC power in watts. So this in milliwatts we have converted it to watts, consistent with the DC power, which is also in watts. So the efficiency is going to be 0.362 or 36.2% as an example. And that's how you find the power added efficiency.